Welcome to my channel Phi Concepts CHM. This is the third part of the series of semiconductor diode characteristics, where we will see about the band structure of an open circuited PN junction. Band structure of an open circuited PN junction. A PN junction is formed by placing P-type and N-type material in intimate contact on an atomic scale. Under these conditions, the Fermi level must be constant throughout the specimen at equilibrium. If this was not so, the transfer of charges would take place until the Fermi levels on the sides line up. This is the Fermi level, which is constant throughout the material. This is the P side and this is the N side. But in N-type semiconductor, the Fermi level EF is closer to the conduction band ECN. So this is ECN. And in P-type semiconductor, it is closer to the valence band EVP. This is EVP. This is the conduction band and this is the valence band for P side, and this is the conduction band and the valence band for the N side. So that is ECP is not equal to ECN and EVP is not equal to EVN. That is, there is a shift in energy levels in a PN junction as shown in the figure. So we'll write down E0, which is equal to ECP minus ECN. So ECP minus ECN, ECP minus ECN. This is E0. Same way EVP minus EVN. So this is EVP minus EVN. This height is E0 and that can be written as E1 plus E2. This is also E0. E1 plus E2. Equation 1, where E0 is the potential energy of the electrons at the junction. To find the contact difference of potential, we'll write down EF minus EVP. So EF minus EVP is equal to, this is half EG minus this E1. Same way, this is equation 2, same way we can write down ECN minus EF. So this is ECN minus EF is equal to half EG minus E2. Equation 3. Adding equations 2 and 3 and rearranging, we get EF minus EVP plus ECN minus EF is equal to EG, this half EG plus half EG is EG minus E1 plus E2. So rearranging this equation, we can keep E1 plus E2 on one side and EG we can take on the other side. So we get E0 is equal to E1 plus E2 is equal to EG minus ECN minus EF minus EF minus EVP. Now we will make substitution for this EG, for this bracket and for this bracket. Equation 4. Now we will write down the intrinsic concentration Ni as Ni square is equal to Np, N into P, concentration of electrons into concentration of holes, is equal to Nc into Nv e raised to minus Ec minus Ev upon kT. This Ec minus Ev is the band gap energy Eg. We can take this Nc into Nv on the other side below Ni square, and then you can take the log. So that will be ln NC NV upon Ni square is equal to Eg upon KT. Then the KT can be taken here. Equation 5. Also ECN minus EF is equal to KT into ln NC by ND. This gives a position of EF for an N-type semiconductor. Equation 6. Same way the position of Fermi level for a P-type semiconductor is given as EF minus EVP is equal to KT into ln NV upon NA. Equation 7. So all these equations 5, 6, 7 we will substitute in equation 4 and we get this E0. KT can be taken common here and then using the rules of logarithm this will be KT into ln of NC NV upon Ni square into ND upon NC into NA upon NV. NC and NB will cancel out, so KT into ln of ND NA upon Ni square. Equation 8. Now we can write down from the charge densities in a semiconductor. NN0 is approximately equal to the density of donor ions ND. PN0 is given by Ni square upon ND. Then Pn0 is approximately equal to the density of the acceptor ions and Np0 is Ni square upon Na. Substituting the above equations in equation 8, we get KT into ln Nn0 into 1 upon Np0 or KT into ln of Pp0 into 1 upon Pn0. So finally we get E0 is equal to KT into ln of Pp0 upon Pn0 is equal to KT into ln of Nn0 upon Np0, where the subscripts O represent O or 0 represents the concentration under conditions of thermal equilibrium. Thank you for watching this video.